All right, so now we're into section 2.3. And we're going to learn a new strategy for taking derivatives. Essentially, we're going to learn something that's called the chain rule. And it's used to find derivatives when there is an exponent outside of a parentheses that, is tedious or impossible to clear. So that's when it's used. It's a little premature probably to explain what the chain rule is. The kind of the first half of the section, from problems 1 through 20, I need to develop some theory that you may remember from college algebra, or you may not. My guess is you wouldn't, because it has to do with composition of functions and looking at composition of functions in a special way. So I'm going to do probably the first half of the video is just going to be theory that leads up until help you understand the chain rule, and then ultimately, I guess even without the theory you can do the chain rule, but I'm going to introduce the theory, and then I'll come back to the sheet and write what the chain rule is, and then we will have 4 rules for derivatives, because in section 2.1 we did the power rule, which is kind of the nicest one. Just multiply the exponent by the coefficient, lower the exponent by 1. And then in section 2.2 we did the product rule, when you had things being multiplied. And then we did the derivatives using the quotient rule when we had divisions. And then the chain rule we're going to add to this, and it's going to be for problems that have parentheses with exponents that are kind of tedious to get rid of. So the first 2 groups of problems, like I said, they just help you understand when we get to the definition of the chain rule what it means. So if I look at each of the questions, by themselves, without instructions, this wouldn't tell me to do anything. F of x equals x to the 4th, g of x equals 4x squared plus x minus 5. So that doesn't mean anything by itself, but the instructions tell me what to do. They said find f of g of x and don't simplify your answer. Simplifying your answer is going to make the chain rule, it won't make it obvious how these connect to the chain rule if I simplify. So what I want to do for number 2 is find an unsimplified version of f of g of x. And you'll notice in my instructions I have square brackets instead of these round parentheses. Square brackets and round parentheses have the same function. They mean the same thing, and you can use them interchangeably. Usually if you already have a round parentheses inside of another parentheses, you don't stack parentheses and you start changing the shapes. So I probably, when I wrote this, when I wrote the instructions, the only reason I put a square bracket in is just because I'm already using round parentheses. These 2 things will have the same meaning. And what they want me to do is what we're going to do is we're going to take the f function and replace its x with the g of x function. So the f function is x to the 4th, and so I'm going to take the x from the f function and get rid of it, put a parentheses where the x was, leave the exponent that the f had outside the parentheses, and then inside the parentheses I'm going to write what the g function is. So f of g of x is going to be 4x squared plus x minus 5 to the 4th. And that's all I want to do for problems 1 through 10, is just get in the process of knowing how to do f composed with g of x. And then in the middle group of problems, we're going to be given something like the answer, something that has something inside of parentheses with an exponent, and we're going to deconstruct it to figure out what f and g would compose to be it. This is called composition of functions. I read this as f composed with g of x or f of g of x. So that's all there was to do for problem 1. If you were problem 2, if you were doing your problem 1, you would say f composed with g of x, either with a round bracket or a square bracket. You'd write the f function without the x, leave a parentheses where the x was, put the g function inside the parentheses. So these are going to go really fast, unlike most problems this semester. So that's all there was to do for numbers 1 and 2. I'm going to rip through most of these problems, and I'll use parentheses to get started in all of them, but the parentheses won't always be necessary. So to do f of g of x for my number 4, I'm going to write the f function, which is the cube root of x, without the x, and I can leave a parentheses where the x was. It kind of turns out that the cube root sign is working like a parentheses, and I don't really need the parentheses here, but it's okay to have the parentheses. And so I wrote the f function without the x, I put a parentheses where the x was, and inside the parentheses I want to put the right-hand side of the g function, which is 3x minus 1. I certainly don't have to simplify this, but I could. And in terms of, I can write it without the parentheses, or I can write it with a fraction exponent, because in my little narrative at the beginning I said the chain rule is for problems that have exponents that are a nuisance to clear, and this problem, had I left the parentheses and put an exponent outside that parentheses, I could get rid of the radical by making a fraction exponent, and this problem, it really is a problem that has a parentheses with an exponent. The chain rule is going to be used to find derivatives of things that look like I have a parentheses with an exponent, a parentheses with an exponent that I really don't care to clear. To clear this, I would have to multiply this by itself 3 times. That's insane. To get rid of this exponent, I have to multiply this by itself 4 times. I don't care to do that. This flat out doesn't reduce. I don't know how to reduce that. It's non-reducible. So the chain rule is going to be the thing that we're going to use to take derivatives when you have a parentheses with an exponent that's a nuisance to clear. And so probably writing my answer to problem 4, even though I said don't simplify, probably writing my answer to number 4 with the parentheses is probably the best thing to do, because it's going to make the connection between this composition of functions and the chain rule probably as clear as it can be. So to do 5 and 6, I'm going to write f composed with g of x, and notice I'm kind of interchanging the round and the square brackets. They don't matter. It's kind of whatever you feel comfortable with. Now I'm going to write the f function without the x, and I'm going to leave a parentheses where the x was, and write the exponent outside the parentheses. Inside the parentheses, I'm going to write x squared plus 4. This is going to be something that we're going to want to, if I want to find the derivative of this, it's going to be something that the chain rule is going to be used for. The chain rule works beautiful to take derivatives when you have a parentheses with an exponent outside of them. Eight's a little almost premature. We're not going to work with E quite yet, but I'm doing f of g of x. I'm writing the f function without the x. I'm leaving a parentheses where the x was, and where the x was, I'm not going to get an exponent because that x doesn't have an exponent. Its exponent is just 1. And where the x was, I'm going to put the g function. It turns out that when we do derivatives with E, which I think is in chapter 3, you're going to need the chain rule to use the derivatives with E. And this is almost out of place, but it's good practice. I really don't need these parentheses. I could have written this as just e to the 4x squared plus x minus 5 power. The Parentheses absolutely not necessary here. And we don't really want to dwell on e's because they're not going to come up today. Similarly, for 9 and 10, we're going to see ln's, and that's a little premature too, but we still can work the chain rule, and that's just want us to get, or the working composition of functions, just want to get us used to that. So for number 10, if I did f of g of x, I'm going to write the f function, ln of x, without the x, and then where the x was, I'm going to put the right side of the g function, which is 2x minus 7. Alright, so that's the first group of problems. The next group of problems is going to give us a problem that most of them have parentheses with exponents, and we have to figure out an f of x and a g of x that would compose to that. And it's not particularly hard. So each of the functions between 11 and 20 are called h of x, and they are the result of composing an f function and a g function. And I'm supposed to find the f and the g function and compose them to show you that they equal h of x. And this is really easy. The g function is going to be the inside of the parentheses, and the f function, you'll change the inside of the parentheses to an x. This is just going backwards. So I'm going to create two functions that would compose to be that function. So I need a function that's called f of x and a function that's called g of x. The f of x is just going to be the inside of the parentheses. The f of x, I'm going to take the inside of the parentheses and change it back to an x. I'm going to drop the parentheses. So for each of the problems between 11 and 20, if there's a parentheses, the inside of the parentheses I'm going to call g of x. I'm going to remove that parentheses and change it to an x. I'm going to call that f of x. And now I'm going to do that composition. I'm going to go f composed with g of x, and it's supposed to equal the original problem. Well, f composed with g of x, I take the function x cubed, write it without the x, leave an exponent of 3, and then inside the parentheses, I put the right side of the g function. That's exactly the original function. So I've deconstructed the h function into two functions that when you compose them, you get that function. That's what 11 through 20 want me to do. And again, they should go pretty quickly. Anytime you have a parentheses, the inside of the parentheses is going to be the g of x. Scratch the parentheses out and change it, or change the inside of the parentheses to an x, or delete the parentheses and you get the f function. For number 12, g of x is going to be the inside of the parentheses. I'll do it with the parentheses, but you don't have to write the parentheses. The f of x, you're going to delete the parentheses and change them to an x and leave the exponent. Now I want to make sure when I do f composed with g of x that I get that h of x. So if I do f of g of x, I write the f function without the x, leave a parentheses where it was, where the x was, and inside the parentheses goes the right-hand side of the g function, which is x minus 2. So none of the first 20 problems make their way onto the test. So I'm not even being too picky about saying this is the answer, this is the answer. Technically for 14, this is the whole answer. It was asking me to find the f function and the g function that compose to be the h function. Similarly, my answer to 12 was this. I was just checking to make sure my answer was right, because it's supposed to find two functions such that h of x equals f composed with g of x. And I'm just checking to make sure I'm correct. Alright, so when you have radicals, you generally make the g function the underside of the radical. I don't have a parentheses here, but a radical almost works like a parentheses. So I'm going to make the g of x the underside of the radical, and the f of x, what I'd get if I change the underside of the change whatever g of x is to just an x. So I'm going to make the cubed root of x. So all I do is whatever I make g of x, I take away and put an x in its place. And again, this is the answer to number 16. I want to check to make sure I did this right. So I'm going to do f composed with g of x. To do that, I write the f function without the x. I leave a parentheses where the x was. Inside the parentheses, I put the right side of the g function. And that parentheses, because I already have the kind of the separating symbol, the radical symbol, that parentheses can be dropped. (17) and 18, there's multiple parentheses. That's not a problem. I'm going to do, as long as the insides of the parentheses are the same. I'm going to make g of x the insides of the parentheses, which are x minus 1. I'm going to make f of x the original problem with the g of x changed to x. So f of x, I'm going to change this g of x, x to an x. I'm going to change that g of x to an x. So my f of x is going to be 4x squared plus 6x plus 4. Let me double check this. I'm going to go f composed with g of x. So this is the answer. Underneath it's my check to make sure my answer is right. To do f composed with g of x, I'm going to go 4 and then parentheses squared plus 6 and then parentheses plus 4, because I write the f function without its x and create parentheses where the x was, and inside the parentheses I put the right side of the g function, which is x minus 1. So I'm done. I've even checked my work because f composed with g of x equals h of x, and that was what was supposed to happen. Last two problems, 19 and 20, till we get to the derivative itself. All right, so g of x has to be the inside of the parentheses, and this only works if the parentheses are equal to each other. If you have two parentheses and they have different insides, then you can't use this strategy. And the f of x is going to be, it's going to have the 11. That parentheses is going to be changed to an x. I'm going to keep the exponent of 3 plus 3. This parentheses is going to change to an x. I'm going to leave the exponent of 2, and that minus 2 just changes. Done with the problem. This is my answer, but I'm going to check it real quick by going f of g of x. To do f of g of x, I'd write 11 parentheses cubed plus 3 parentheses squared minus 2. I'd write the f function without the x's, and in place of the x's I left a parentheses. Inside the parentheses I write the right side of the g function. And that is exactly the original problem, and that's what I need to do. I needed to deconstruct the h of x into two functions.